Hello everybody, this is CIS 250, Introduction Assembly Language, the part B of the lecture going over floating point. And so the floating point, to do floating point operations, there's an additional part of the processor. So if you remember from the early days of class, we had the ALU. On top of that, on the processor, there's also the FPU, which is the floating point unit. And so the ALU does all the integer operations. The FPU is going to do all the floating point operations. And this was introduced way back in the 80s on the 87 processor, basically to do floating point arithmetic. So before then, the floating point math was just done on the ALUs. And then, so to do FPU stuff, you're going to use different mnemonics than you would for the ALU operations, or the general purpose register operations. And also, you have a different register as well. So you have a floating point register that acts like a queue. So basically, there's additional for the FPU additional stuff. You have both the additional registers as well as the different processing unit on the chip just for FPU. So there's going to be a different set of mnemonics specifically for doing floating point operations, which tells the processor to use the FPU and floating point registers. And so, like I mentioned on the previous slide, the FPU does not have a general purpose registers like AX, EBX. The FPU uses, instead of Q, it uses a stack. And so the value, basically the values are loaded from memory into the FPU stack. And the FPU stack only can hold 8 values, and it kind of rotates and it acts like a, I would say like a Ferris wheel, where the top of the stack is always the FP stack, or the floating point stack 0. But if you push or pop that value, if you pop it, that value doesn't go off the stack. It just rotates to the 7th element, or the end of the stack. And then for operations for the FPU, we use the postfix format. So the postfix format, which I'll describe in the next slide, basically is a way to do the order of operations, to kind of calculate the order of operations for your computer program. So the postfix format basically has the order of operations where you have the numbers and then the operation, then a number, and then the operation. So parenthetical 5 times 6 plus 4 becomes 5/6 multiplied by 4 plus. So you can see if you do these numbers, this becomes 5. You put 5 and 6 into the stack, multiply those two, pop those values out and multiply them. That becomes 30, plus 30 back into the stack, put 4 into the stack, and then add those two numbers together. So that it becomes 34. Or if you have a parenthetical 4 plus 3 times parenthetical 2 plus 5, you push 4 and 3 into the stack, and then when you see the operator, you pop the top two numbers, 5 and 2 in the stack, push those in, push that number in, so you have 7 and 7 in the stack. You multiply those together, you get 49. And so again, 5 times 6 divided by 4, parenthetical 4 divided by 5, you'd have 5, 6, push on the stack, pop, 5, 6, pop, 5, 6 from the stack, multiply them together, push the 30 back in the stack. Then 4 minus 5, you have negative 1, and divide this, and it should be negative 30. So if I'm going to do 4 plus 5 in parenthetical, divided by parenthetical, 2 minus 1 times 4, in postfix, this would be 4, 5, and then addition, add, and then the parentheticals, so 2, 1, minus, and then multiply, and then divide. So the FPU registers are going to be the opcode register, which stores the last opcode, which is basically the last the hex value for the last operation. The control register, which handles the precision and rounding rules, which we'll cover later. The tag register, it basically indicates the contents of the FPU register. the last instruction pointer, and then the data pointer. So it's kind of just pointing to different locations in it. These are additional registers. The only one we're really going to care about we're really going to get into in this class is the control register, which we'll talk about the precision rules later. And so basically in the control register, we're going to have the FPU rounding. So there's basically 4 ways to do rounding. So normally rounding is, if you have a number, the last significant digit, the one after the last significant digit, if it's a 5 or above, you round up. If it's 4 or below, you round down. Well, for FPU rounding, basically we can set the ways we want to round. And so if you set in the control register the 0, 0 for the rounding bits, it's basically going to round to the nearest even. So basically it's going to either, if the last digit is a 1, it's going to round, the last significant digit is a 1, it's going to round up. If the last significant digit is a 0, it's going to round down. If you have the 0, 1, so it's going to always round towards negative infinity. So if it's a positive number, it's going to round towards 0. If it's a negative number, it's going to round down to basically towards infinity. So the number would actually increase in absolute value. If you have the 1, 0, that means it's going to round towards positive infinity. So if it's a negative number, it's going to round towards 0. If it's a positive number, it's always going to round up to the higher absolute value. And then if you have 1, 1 in the binary, it's always going to round towards 0. So if it's a positive number, it's always going to round down. If it's a negative number, it's going to round up towards 0, essentially. And then there's built into the FPU, there's a set of constants. And so these numbers basically have predefined values. We have 1 and 0, or kind of common ones, and pi. But we also have to kind of make math operations easier. We have log 2, 10, basically log 2 of natural log 10 of 2, and then the natural log, or 10 of log of e. And so these are basically 1 and 0 are the main ones you probably use, and maybe pi. These other ones are basically to kind of make kind of higher level math operations easier. But if you ever look in source code, 1 and 0 are usually the only ones that really are used. These other ones are maybe used kind of at the lower levels, but I've never seen them used in basically like C or C++ or anything like that. And so FPU has a similar instruction set to the general purpose functions. They kind of operate in the same way. You have add, subtract, multiply, divide. The main exception is FPU is going to use the stack instead of loading stuff from a general purpose registers. So one of the initial operations is the fint, which initializes the FPU. Basically, it masks all the rounding point exceptions, makes them all 0, sets the rounding to the nearest even, so it's kind of the default value, and sets the precision to 64 bits. So it basically just kind of initiates everything for you. If you don't set this, some of those values might be kind of wonky when you start running the software. And so the value types in the FPU is a Q word, which is just really it's a quadruple word. It's basically a long integer. The T byte, which is a 10-byte number. So it's an 80-bit integer. That's what the T stands for, 10. And so it's just a little bit bigger number. The ones we really care about, the FPU numbers. So we have real 4, which is a 32-bit number. So you can think of this as a single precision number. You have the real 8, which is a 64-bit number, which you can think of as a double in like most programming languages, or double precision. And the real 10, I've only really seen this in C#, but it's an 80-bit real number. So you basically get a little bit more precision. Remember in the last class we talked about how 32-bit and 64-bit numbers are set in memory. The 80-bit number kind of does a similar thing. And so to load the numbers in, we have the FLD, which the instruction stands for floating point load. This basically just pushes a value onto the top of the stack. So say if I have the value, so I initialize the data with double 1. So I both have these as double precision numbers. I have 234.56 and then 10.1. And if I do FLD double 1, I'm going to put 234.5 on the stack at slot 0. And if I do FLD double 2, I'm going to move from memory. 10.0 is going to go on the top of the stack, which is ST0. So the top of the stack is always going to be FT0. And then when you push the value down, it's going to go to the lower number. So notice here we have 10.1 was just the number pushed onto the stack, and then ST1 was the previous ST0, and that gets pushed down. And we have a few other load commands. We have FILD, which converts an integer to a double and then loads it to the top of the stack. We have FLD1, which pushes 1 into the stack. FLD2T pushes the log 2, and then all these other values, kind of the main ones. FLD pi, so these are the preconceived values, will push pi into the stack, and FLD0 pushes 0 onto the stack. And then to get values off the stack, if you do FST, it moves the value from the top of the stack into the RAM. So if I do FST double 3, what this is going to do is write the value on top of the stack, which is ST0, into the memory location. However, the stack is not popped. So if you want to load the value off the stack and store it, you do FSTP, which pops the value, which not only stores the value, it pops the value on top off the stack. And then for the arithmetic, we have these basic values. We have FSH, which changes the sign, so basically flips the sign. We have FAdd, FR, FSubtract, which subtracts the source from the destination. Multiply multiplies the top two numbers together. FDivide divides the destination by the source, so it's first number by the second number. And then this should be FDivideR, divides the source by the destination. And then we have FCompare, which basically compares the two values together. And so this is basically the same as CMP in the ALU. Essentially, you can do this for comparing numbers for basically for doing comparisons, and then use basically use the same jump commands as before. So what I'll go on now is to show you some code of kind of how this works in action. And notice how it stops here. So in the registers, we can actually make this a little bit more. We can actually, if you right-click on this, on the registers, and then look at floating point, you can actually see the floating point. Try to. Actually, the floating point registers. So notice here what I'm going to do is I've initialized the values. So we still have the regular registers, but we also have the storage values. So I'm going to do a step here. And notice the only thing that changes the control value, so basically clear the control stuff. And then I'm going to do FLD, so it's going to load the first value from memory. So it loads 234.5, and notice how it's stored in scientific notation. And we have some of these tags up here. FLD2, so notice here how I have our three numbers. I have 23.5, and then it has 2 here. So notice how the first number pushed in goes to storage point 1 and then storage point 0. And then I'm going to multiply these two values together. So what it does is it's going to pop both values and then put the top value. So 20 times 235 is going to go here. But also notice how since it popped the value, it doesn't actually come off the stack. It just gets pushed around into storage point 7. And then finally I'm going to push in FLD for real 3. And it pushes the 15.5 in there. It's going to multiply this number, and then when I subtract this, it's going to subtract these numbers from each other. And notice how it just subtracts the value in ST0 from ST1 and puts the difference in ST0. And then notice how it writes over this value here because it popped it twice and then wrote the value in. So that's all I really have for today's lecture. I hope you guys have a nice week, and then I'll be making a video describing what to do for Lab 3.